Vanakkam. Welcome to this course on biomedical instrumentation. We have been looking at electrode theory, various types of electrodes, consideration for practical recording electrodes, etc. It looks more like we will not be able to complete the entire electrode theory in this week's content. It looks like it will spill over to the next week. So, we will do what we can within this week. The rest of the electrode theory we will continue in week 6, the next week. But the entire syllabus will be part of the exam syllabus. Okay. So, let us continue our discussion. So far we have been looking at polarizable, non-polarizable electrodes, silver chloride electrodes, etc. In this video, we will look at a special type of electrode called as microelectrodes. Microelectrodes means size, really small sized electrode, micro in size. That is, those electrodes whose dimensions are in the order of 1 micron or less, or in few microns to few tens of microns maximum, are called as microelectrodes, really small electrodes. There are many challenges that come with having electrodes of such small size. One immediate observation as an electrical engineer or as someone with understanding of high school physics, immediately you know when some wire is really small, its resistance is going to be very high. So, impedance is going to be a huge problem in this case. So, we discuss this and other aspects in this class. So, types of microelectrodes, metal microelectrodes, supported metal microelectrodes, micropipette electrodes, and electrical properties, electrical equivalent circuits, etc. for these microelectrodes. So, what are these? What is our interest? Why do we need this? We need this because we are interested in studying electrophysiology of excitable cells. Essentially, this is the foundational pillar for modern neurophysiology. So, if I am interested in making intracellular recordings from within neurons, then this is an indispensable tool, right, for studying electrophysiology of excitable cells or neurophysiological recordings, intracellular recordings, particularly to measure potential differences across cell membranes at the level of cells. So, essentially what do you want? What you are looking at is a device that can record from within the cell without damaging the cell. Now, how is that possible? Because this device, this electrode will have to penetrate the cell membrane to record from inside the cell. Imagine, just try to imagine, let us say I have a set of AA batteries, say nowadays packs of 32 batteries are sold, a pack of 32 batteries are there, and I am interested in measuring the voltage from the terminals of one of these batteries, exactly when there are a bunch of these batteries available, one on top, they are stacked on top. Let us say there is a 16 batteries stacked in a 4x4 configuration. There are 4 batteries, 1, 2, 3, 4, and on each of these 4 batteries are kept, right. 16 batteries are kept like this. I would like to measure from one of this, and I know which one exactly. Now, that is the challenge. Now, how do you do that? These are stacked and you will have to access that particular, those two terminals, and then when you connect a voltmeter, you are going to measure the voltage. Oh, that is so simple and trivial, except that your measuring device will have to be, the tip will have to be 1,000th the size of a grain of salt or something like that, really tiny, except it is not measuring from an alkaline battery or a regular battery. It is 1 millionth that size, perhaps, give or take, or at least 1/100,000th that size. So, really tiny when compared to the cell dimensions. So, you are looking at nano scale. This is necessary to avoid injury to the cells, because if you injure the cell, then it is not clear what is it that you are measuring. So, that cell's behavior is not affected by the recording. Any method that you use to record should not affect the phenomenon that you are attempting to record, very critical. Okay. So, they need to be really tiny when compared to the cell dimensions first. Yet, it should be strong enough to penetrate the cell membrane. If it is flimsy, then it cannot possibly penetrate the cell membrane and be mechanically stable to remain in position and not get displaced. When I am making the measurement, it should not get displaced due to some flow or due to some physiological phenomenon. That should not happen. So, the dimensions of interest are from 0.05 microns to 10 microns. Now, let us try to analyze this. 1 micron is 10 power minus 6, 0.1 micron is 10 power minus 7, 0.05 is 5 into 10 power minus 8 meters, or it is actually 50 nanometers. That is the size you are looking at. It is anywhere from 50 nanometers to 10 microns in diameter. That is the size of your microelectrodes. And there are 3 distinct types. One is the solid metal electrodes, those that are metal throughout that, and those that are made from metal within or on the surface of a glass needle. I have a glass needle and inside I have coated it with metal or salt of a metal. It can be silver chloride coating, that is possible, or it can be a micro pipette of nanoscale size that is filled with an electrolyte solution, using which I can measure. Remember, what is it that you are trying to do? Your aim is to measure potentials across biological batteries. Excitable cells are biological batteries in the sense that because there is a steady potential difference, like you are having a battery, let us take a AA battery or a AAA battery, across its 2 terminals you are going to have a steady potential difference. Likewise, there is a steady potential difference across the cell membrane of a excitable cell. Essentially, these can be characterized as biological batteries. These are living batteries. So, I would like to measure potentials continuously for a long time, over a period of time. Long, what does it mean in neurophysiology? What is long? Minutes to hours is considered long. Minutes to hours is years in human terms. In neurophysiology, minutes is several years. So, because in neurophysiology we are looking at millisecond resolution in time. So, we are looking at measurement of these potentials in live biological batteries. How do we do that? That is the question. Right. First is the use of metal microelectrodes. So, what you have is a lead wire. So, that is here, and there is a mechanical supporting shaft that ensures that this electrode stays in shape and does not become flimsy. So, there is a mechanical shaft, that is a supporting shaft, and there is an insulation. Only the tip is uninsulated. At the tip there is a little bit of insulation removed. Everywhere else there is insulation provided. So, that is the metal microelectrode. Usually made of a relatively small or fine metal needle that is insulated everywhere except for the extreme tip. Fine or ultra fine means, what is the size? 50 nanometer to 10 microns, several tens of nanometers to about several units of microns. That is what you are looking at. The exposed tip is the only part that is measuring the activity. Of course, the insulation will not measure. How do you fabricate this? You fabricate this using a process called electrolytic etching. Okay. So, essentially you placed this metal needle as an anode in an electrochemical cell and a current is applied. This etches the needle as it is slowly withdrawn from the electrode. You slowly gradually withdrawn, it becomes thinner and thinner, forming a really sharp tip. This. It is a process that requires an enormous amount of skill and patience to achieve. Critical to note is that no two electrodes at this scale is likely to be of the same dimensions or have the same characteristics. Why? Because it is unlikely that I am going to get similar tolerances at the scales at which I am working, especially if humans are involved in the fabrication process. Even otherwise, tolerances even with machines and robots are not going to be so good that you are going to have consistent output within and across batches. I am making many electrodes in a batch and I am making many such batches. Consistent output, or output in the sense consistent dimensions and electrical characteristics of the electrode across and within a batch is very difficult to achieve, extremely difficult to achieve. What are the materials used? Typically materials such as stainless steel are used, and platinum iridium alloy is used quite frequently, and tungsten are used for their strength because these are strong. Right. Tungsten carbide is also commonly used because of its exceptional durability. It is going to last for a long time. Right. Then it is supported, then you need to find a way to support, mechanically support this. Then this etched needle is supported by a large metallic shaft that then provides stability, mechanical stability and support, mechanical support and electrical connection. Then you are insulating it with some polymer material or varnish. You just coat it with varnish, paint it, coat it with varnish, leaving only the tip that is exposed for electrical contact. So, again this picture I have taken and adapted from the famous Webster book. Then I have supported metal microelectrodes. In this case, it is not the metal that is directly there. Instead, I have a metal, but the insulating material is supported, for example, with a glass covering, right, where strong insulating material provides a mechanical support and the metal itself acts as the contact point. Only the tip is exposed. Everywhere else there is insulation. Here there is insulation, here there is insulation. Only at the tip, here there is insulation, and on this side there is insulation. Only where there is a blue circle, that is where alone there is the exposure of the metal. Right. There are many ways of fabricating this. One is a popular way of fabricating this is the metal filled micropipettes. A glass tube is filled with a low melting point metal, and then this tube is heated. I have a low melting point metal, and then this tube is heated to a point where this becomes softening point of the glass, and then you stretch it. Once again, skill is critical in these kind of processes, and then you stretch it so that it becomes narrower and narrower to the point where, to the size of your interest, right. This constricted tube is then broken at the narrowest point, forming two micropipettes that are filled with metals. And this glass essentially is, once it is cooled, will serve as an excellent insulation, also as an excellent mechanical support, right. But the exposed tip will continue to be a good conductor as the active electrode. What are the common metals used in this process? Silver solder alloys, platinum silver alloys, and other low melting point alloys such as iridium. The other approach towards making supported metal microelectrodes is to draw a really small solid glass rod to form a small or micro pipette. Then instead of having solid metal inside this glass, you are essentially going to have coating, deposition of a thin film, preferably uniformly. Again, this uniform deposition is hard to achieve. Coating or deposition on the surface of the glass, uniform deposition on the surface of the glass. Then you insulate it using a polymer. Now what you have, and then only the tip alone, you pull the tip alone and expose that as the recording tip, only the tip that is exposed for measurements. Now the metal film's thickness is typically in the range of hundreds of nanometer or tenths, not tenths, tenths means 1 by 10 of 1 micron, that is 0.1 micron or 100 nanometer. This is the method in which you are having a glass micropipette that is coated with metal film as opposed to deposited inside the pipette. This is, then you have the micropipette electrode. In this case, what you do is you have a capillary tube that is heated to a softening point. Then this softened glass is very quickly stretched to produce a constriction, to make it really narrow, and then this tube is broken at the constriction, right, essentially forming a micropipette like this, right, like this, with a tip of diameter approximately 1 micron. This is approximately 1 micron. This diameter is approximately 1 micron. Now, what you need is a tool that is essentially a microelectrode pullers that are used to quickly heat and quickly stretch. So, you need an electromechanical device that will quickly heat, simultaneously a thermo-electromechanical device that will heat and quickly pull. These are specialized microelectrode pullers that are used to heat and stretch the glass capillary uniformly, ensuring relatively, so this method is a relatively consistent, reproducible method. Now, then what you do, unlike the previous cases where you deposit metal itself, in this case you fill this hollow micropipette with an electrolyte, typically 3M potassium chloride, and then at the other end of the micropipette you place a metal electrode inside that is in contact with the electrolyte solution. This metal electrode is usually made of silver wire that is prepared with electrolytic silver chloride. This is essentially silver chloride electrode. Occasionally you can also use platinum and stainless steel wires that are used for this purpose. Stainless steel is not a metal, it is essentially an alloy, does not matter, it is still a conductor. And then you use a cap, to seal, otherwise the electrolyte will leak, to seal the micropipette to secure the metal electrode and maintain the structure and the composition of the electrolyte. What are the advantages? The advantages is that it is ideal for, because it can be really small, it is extraordinarily small and ideal for intracellular measurements because of their small tip size, and can provide relatively stable measurements with relatively minimal damage to the cell, because it is not made of metal but rather made of glass, right. But it is the electrolyte that is the conducting, that is going to do the measurement, right. Yes. Then finally what you have is microelectrodes that are based on microelectronic technology. Now in this case what you do is you use microelectronic technologies, methods that are used in the fabrication of electronic chips and electronic integrated circuits and other such chips, large scale integrated circuits, VLSI type of chips. What are the technologies that you use from our basic high school physics and some basic electrical engineering knowledge? We know that a popular method is called photolithography. Is it mentioned in this slide? If it is not mentioned in this slide, learn what this is on your own. So, what is the method? You have a narrow gold strip. One method, one approach is to use gold strips and silicon dioxide insulation. You have a narrow gold strips that are deposited on a silicon substrate, which is having a silicon dioxide film to insulate the surface. These gold strips are then further insulated by another layer of this. So, for example, here is a silicon substrate, on top of that I have silicon dioxide or silica insulated AU probes. AU means gold probes. This is one method. The other is to have a silicon probe like this that are having several of these conducting leads that are exposed to this. That is the other method. So, second method is to use etching to form tips. In this case, silicon substrate is etched into a relatively thin, narrow structure to house the gold strips. So, you are going to use, how do you do this etching? That is photolithography. Silicon is etched a few millimeters back from the tip, so leaving only the gold strips. So, etching is done such that only the gold tips and the insulation are exposed at the distal most point. Only the gold tips are exposed, using helping us use them as electrodes essentially. Then this insulation at the end, insulation is, what is the insulation? Silicon dioxide at the end is then etched away at the tip to expose the gold strips, essentially providing the electrical contact and the opportunity to make measurements. A similar approach is used for example, several channels through which several electrodes and leads can go. Another approach for this is the up and coming technology. This is the future of this field. Microelectrodes that are made out of microelectronic technology and photolithography. Right? What are the advantages? While these are not, you might think that these are actually smaller than micropipettes. They are not actually, because micropipettes are made of pure glass, and it is the electrolyte that is acting as the electrode in that case, right. In this case, they are not as small as micropipette electrodes. These are essentially useful for what are called as electrode arrays, microelectrode arrays, multi-electrode arrays, when I am interested in measuring from multiple sites. And I have a relatively great control over the geometry of the tip and the consistency across electrodes in an electrode array, because this is using this microelectronic technology. This is used frequently to measure from multiple neurons inside the brain. So, of live behaving animals, of live behaving humans, for example, arrays of multi-site electrodes can be mounted on these thin silicon probes to detect local potentials, not necessarily from individual neurons, but from multiple sites, because because of the size, because of which area from where you are recording, neurons may be smaller than the size of these electrodes, in which case you are essentially still going to be measuring from local field potentials of several neurons. But still you might be measuring from, if you are using an array, several neurons here, several neurons here, several neurons here, several neurons here, several neurons here. So, several such local field potentials you can measure, right, quite frequently used in neuroscience research. And the other approach is to use small chambers, electrodes that are made of gold or silver chloride, that are housed in insulating films with relatively small openings. These are then filled with electrolytes like sodium chloride that then interact with the neuronal tissues. Then what you have are sieve microelectrodes that are used in peripheral neural studies. Right. These are channels that are etched through silicon chips that allow neuronal regeneration and growth. Again, what is the metal that is used? Gold metallization around these channels that provide electrical contact. So, that is the approach that is used in this case. What are some of the electrical properties of these? Resistances. Resistance, what are the various components of the equivalent circuit? What is so this is the equivalent circuit of a microelectrode, right. This is an equivalent circuit of a microelectrode. Now, what are the various components of this equivalent circuit? First is resistances. resistance Rs essentially represents the resistance of the microelectrode itself. It is essentially, it is going to be great, it is particularly significant in the shank and the tip region, where because the ratio of the length to cross sectional area will be very high, because it is going to be really small, teeny tiny at the tip and at the shank. It is not going to be that, it is going to be much thicker. So, that means the resistance is going to be huge at the shank and the tip relative to the size, whereas much smaller at the rest of the electrode. Right. Then capacitance is essentially distributed. Why is this capacitance distributed? Because you are going to have either glass or some insulation. So, you are going to have a form of distributed capacitance that is going to be present per unit length. Of course, not in meter, in this case millimeter, does not matter, whatever is some unit of length. And this distributed capacitance can be modeled as diameter of the insulated electrode and the diameter of the metal electrode itself play a role in this. So, essentially the CD2 by L is 2 pi epsilon r epsilon naught, where epsilon r is the relative permittivity of the insulation material. Epsilon naught is of course the permittivity, not permittivity, it is rather only one T is the permittivity of the free space. Epsilon naught is the permittivity of free space, epsilon r is the relative permittivity of the insulation material. And then the shaft region itself can be modeled as a parallel plate capacitor, in which case I can essentially model this as epsilon r epsilon naught d divided by the T, where T is the thickness of the insulator. Right. Now, let us look at a numerical. Now, let us look at a numerical where we are interested in computing the capacitance. It is a simple problem where a microelectrode has a tip area of 2 micrometer squared, not 2 microns, 2 micrometer squared. A is 2 micrometer squared separated by 1 micrometer of electrolyte. So, D is 1 micrometer and epsilon is 80 into 8.85 into 10 power minus 12 farad per meter. This is epsilon. Now, what is C? C is epsilon A by D. Now, I could not this D, rather small d, I could write this as 80 into 8.85 into 10 power minus 12 into 2 into 10 power minus 6 epsilon A, because 2 into 10 power minus 6 meter squared divided by D, which is 1 into 10 power minus 6 microns, is it not? 1 micron. 2 into 10 power micrometer squared is essentially, you could 2 micrometer squared. So, that would actually be 2 into 10 power minus 12, is it not? Check this. So, after some computation, I will essentially end up with 1.416 femtofarads, very small capacitance, but it still plays a critical role in the computation. Please check whether this is correct. Now, where will this play a critical role? In the frequency response. In the high frequency response, this will play a critical role, because capacitance comes into the picture during the frequency response of the entire system. Okay. Let us continue our discussion of microelectrodes. We were looking at the equivalent circuits. So, what do you have? You are having a cell membrane, you are having a cell membrane that is tipped, and then there is an insulation, and then there is a metal rod, and there is a reference electrode on the outside in the extracellular, and then you are measuring a voltmeter, using a voltmeter. See, what is the voltage of intercells? You are essentially what are these microelectrodes? These are essentially nano voltmeters of nano size. These are not nano voltmeters, but rather nano sized voltmeters, right? This is what is of interest for us. So, this can be modeled as membrane potential and action potential. This is the battery whose potential I am trying to measure, and then I have a series resistance, I have a resistance and capacitance that is due to the microelectrode itself. Then I have another potential. Do check this circuit, and I have adapted this circuit from, of course, from the famous Webster's medical instrumentation textbook. Right. Critically, what is the impedance behavior of this? There is going to be frequency dependent impedance. Typically, it is going to range between 10 and 100 mega ohms. Another one thing I could do is to increase the surface area, because if I increase the surface area, effective, for example, I could use platinum black and use it to coat to increase the effective tip area, reducing the impedance at lower frequencies. Or I can use silver chloride coatings to further reduce impedance, but then the problem is that silver chloride coatings are relatively fragile and may release ions that might change the behavior of the cell. But note, as I am increasing, this is a constant trade-off between surface area and impedance, right. If I am having a large surface area, impedance is going to reduce, like that is common sense. But if I keep increasing the surface area, then my spatial resolution, my ability to make multiple measurements in a small space is going to be compromised. So, I am going to compromise spatial resolution in favor of impedance, or I can have a very good spatial resolution, but then the impedance will be very high. So, you need to make your choice, you can't have both, right. The other is the metal electrolyte interface components, RMA, CMA and EMA. These are resistive, capacitive and electrochemical potential contributions of the metal electrolyte. This is the metal electrolyte interface components. These are these, right. And then reference electrode contributions. These are, what are these? These are noted here, RMB and CMB here. Here, for example, RMB, CMB here, and RMA, CMA here, right. And then there is an intracellular resistance and an extracellular resistance, RA and RE, that are there, right. RA and RE, this is RA and there is then RE, that. And then I also have a distributed capacitance associated with the shank and the surrounding fluids. So, there is going to be a distributed capacitance that is there. We have already discussed these internal components, RMA, CMA, EMA, and there is also the resistance of the electrolyte shank and the tip region, and then there is a distributed capacitance. What are the potentials? There are many potentials that are there. There is a liquid potential, liquid junction potential. This arises from the interface between the micropipette electrolyte and the intracellular fluid. So, there are multiple junctions. One is the junction between the intracellular fluid and the electrolyte. The other is the junction between electrolyte or the tip potential, membrane potential due to the thin glass wall at the tip, right. That. And then there is the contribution of intracellular and extracellular potentials, and then there are series resistances that are associated with intracellular and extracellular fluids. Remember that some of these things are not constants. Okay. Some of these things change depending on the state of the cell and the dynamics under which the cell is operating. This is the metal micropipettes and their equivalent circuit components. Again, when you look at the impedance behavior of metal micropipettes, the resistance of the micropipettes are primarily, so essentially the impedance is primarily resistive, ranging from 1 to 100 mega ohms, and because of distributed capacitance and high resistance, essentially this acts as a low pass filter, causing slow response to rapid changes in potential. That means that relatively fast changes cannot be captured by this method. So, you need to know the limitations of the method when you use method. and there are some ways of compensating for that. For example, to counteract the effect of distributed capacitance, you can use positive feedback amplifiers to counteract, improving the time response. You can only do so much of this. Essentially, you are having these summary. Essentially, the metal microelectrodes have tungsten or platinum iridium tip insulated everywhere except at the tip. Primary application is in intracellular and extracellular neural recordings. What is the advantage? Because tungsten, platinum and iridium are relatively highly durable, relatively strong, highly durable, sharp tip and very precise. But then the problem is limitations. It requires an extraordinary amount of skill to fabricate and place. And also consistency across batches is difficult to achieve. Wire in glass, supported metal. In this case, what you have is a low melting point metal such as silver or solder alloys inside pulled glass capillaries, relatively small capillaries. These are used frequently in intracellular recordings and intracellular stimulation frequently. These are insulated by glass, so a sharp tip is achieved by pulling the glass. The disadvantage is that they are very brittle and sensitive to mechanical stress because they are very small, right? So they are going to be brittle. So it's not like the kind of failure that they are going to go through, it's a brittle failure. Then you have metal film on glass. In this case, a thin film is coated or deposited on the glass and then insulated everywhere except the tip, right? In this case, you have precise stimulation or recording arrays. This is suitable for arrays, right? These are reproducible and suitable for arrays. The problem is with this, the fabrication is complex. I have a glass substrate on which I am depositing. Uniform deposition is one challenge, and mechanical strength is questionable because the inner core is made of glass, right? Then I have micropipette glass electrode. In this case, I have a pulled glass tube that is filled with an electrolyte, usually 3M potassium chloride or silver chloride wire inside that. This is very useful for intracellular measurement because it does not cause damage to the cells, minimal damage to the cells, and the tips can be really fine of the order of 1 micron of this. The problem with this is that it is going to have high impedance and relatively fragile and hard to insert because the metal support is no longer there. The support is coming from the electrolyte, and that is problematic. Insertion into the cell is going to be challenging. Otherwise, you are going to have metals that are going to be able to pierce through the cell membrane. That is not going to be possible in this case. Then you have microelectronics based or microfabrication techniques based microelectrodes or silicon based microelectrodes. In this case, what you use is microelectronic technologies. Use gold strips on silicon substrate with silicon dioxide insulation, right? This is quite frequently used for multi-electrode recording arrays or multi-site brain recording or multi-electrode arrays. The advantage is high density arrays of reproducible geometry, chronic for a long time. The limitation is that the tip size is definitely greater than the micropipette case, and fabrication technology is definitely an advanced technology. And then you have sieve electrodes, channels that are etched into silicon with metallized contacts. These are used in peripheral neuronal regeneration studies, and this allows nerve growth through the electrode array. These are used for long term. The limitation is that long term biological integration is not really yet a well established phenomenon. Now, what are some of the limitations that are common across all this? Manufacturing limitations, that is limitations, primarily manufacturing limitations. What are these? Consistency can be poor, or yield rates is poor, high rejection rates, and when you need to sterilize because sometimes you use low melting point alloys and low melting point if you sterilize it in an autoclave, it is possible that the geometry will change because you might be using it in studies that require sterilization across reuses, repeated use, if you sterilize in between and if the electrode changes, then you have essentially lost the electrode. So, because some of the fabrication techniques use low melting point, by design they use low melting point metals, right. So, sterilization is problematic. These are some of the challenges. What are the current approaches, current microelectrode fabrication techniques that are still under research but not yet used on the field? Carbon nanotubes. What is the future looking like? What is the current carbon nanotubes? Carbon nanotubes based electrodes, graphene electrodes, then PEDOT-PSS based electrodes. What is this? It is a conductive polymer. Check what it is. For your own interest, use your own skills, Google or ChatGPT or whatever, and find out what is this PEDOT-PSS based electrodes. And nanowire based arrays, nanowire arrays. These are some of the topics that are coming up in the future or current and future. So, with this we come to the end of this video. In this video we looked at microelectrodes and various types of microelectrodes, metal electrodes, supported metal electrodes, micropipette electrodes, and microelectrodes made using micro electronic technology, photolithography and this, and what are the challenges in manufacturing, and we also looked at what the future looks like. With this we come to the end of this video. Thank you very much for your attention.